The title of this video is Matter Waves, and this is where it gets really interesting. Photons being a wave and a particle, that's easy to buy. But what about an electron which has mass? How about that becoming a wave as well, or has matter and wave duality? And then that means that we can carry this thing over to talk about protons and neutrons, which are the massive part of what we have in matter. Those also can be wave like in nature. So, to start this thing, we have to get into the math. And I wanted just to give you a little visual here of me blabbing, and then I'll go to my drawing pad and we'll start into some of this stuff. Okay, what we want to do is talk about matter waves. So let me see if I can spell matter. And let's put an exclamation point there to show how wonderful this is all. Okay, well, how do we get to matter waves from what we've talked about so far? We talked about the photon as being this thing whose energy was h times f, where f is frequency and h is Planck's constant. Planck's constant is a really tiny number. It's 10 to the minus 34. That's how tiny that one is. And then we have another expression that you might be familiar with. Energy equals kinetic energy 1/2, if you've taken any physics at all, 1/2 mv squared. And that is the, what is that? Potential or kinetic energy? That is the kinetic energy. So I could put kinetic energy, put a K here for kinetic energy. Then we have another thing that even though you might not understand it or you really don't know what it means, they always show this around smart people. Okay, how is this getting to matter waves? Well, let's take these two and bring them together and say that if both of these are energies, what happens if I put HF equal to MC squared? Now, if we're talking about matter, let's say we're going to go after the electron on trying to find out whether electron is a wave. That electron is never going to get to the speed of light. If you've got some mass, you're never going to get to the speed of light. So here's what I'm going to do is change the C to a V. HF equals mass times velocity squared. Then what am I going to do here? That looks very strangely like the kinetic energy up here, doesn't it? 1/2 mv squared. But this is what I'm going to do. This has H max constant in it. And that's really where the quantum mechanics thing takes over. Now, what I'm going to do is represent frequency as another symbol. I'm going to say frequency equals, let me make sure I get it right. Frequency is equal to velocity over wavelength. Let's see if that makes sense. This is in meters per second. This is in meters per second. This is in cycles per second. And so, no, I'm sorry. This is in cycles per second, meters per second. This is in meters. And so the meters will cancel out, and then we'll just get per second, which is frequency. Boy, I had to talk myself through that to make sure what was going on. Now, what I'm going to do is plug in this V over wavelength for the frequency. V, which is still velocity, over wavelength equals to mv squared. And now bear with me. What I'm going to do is multiply both sides times wavelength so that I've got wavelength in the numerator over here. And then I'm going to divide both sides by mv squared, which will give me hv over mv squared. Now, where am I headed? What's the final step here? Well, the final step is going to be, I'll put the wavelength over on this side, and you'll see that the velocities cancel out. So I've got wavelength equals h over mv. That means this is the wavelength of some mass that is moving at a certain velocity. If that mass isn't moving at all, then what's the wavelength going to be? Well, if the velocity is zero, then the wavelength is infinite. So no wave matter unless you've got this thing moving. Now let's see what the wavelength is going to be if I'm moving at some velocity. Well, as that velocity increases, then the wavelength is going to start going down. And so here we've related a piece of matter to wavelength that it has. Let's see if there's anything else in there. See, there's no frequencies. There is a frequency. This is the wavelength. So this relationship is a big deal. And that's what this guy, whoops, I always capitalize that, and I shouldn't. That's what this guy, Frenchman, hope I spelled his name right, de Broglie, and he came up with this idea of matter waves, and that's where it all takes off, and we get the waves into the matter.